Dear participants, in this session, we will be concentrating on a particular method, rather an optical switching method to determine RPM of a rotating shaft. You see, for this, we will be employing this DC motor. This is a 12 volt DC motor which is connected to a PWM source by which I can control rotation of this shaft. There is a very simple electronics over here, and this is the slotted optical switch. These two housings you can find. This is the slotted optical switch that we can employ, that we are actually employing here to generate a frequency signal. As the shaft will rotate, a frequency signal will be generated at the output pin. You can see there is a connector. A 3-pin connector is given. This is the 3-pin connector. I will maybe put off the light so that you can see clearly. This is the 3-pin connector. You can see, and one of the terminals should go to 12 volt supply, which is plus, other is minus, and in between these two there is the output terminal. Okay, there is a transistor and some resistances have been used. Okay, so let us now look closely to the slotted optical switch arrangement. You can see here, this is a plastic housing in which one of the component that is housed is an IR diode and the other component is a phototransistor. You can see over here, if you look closely, I don't know whether it will be visible or not. Yes, you can see on one of the top side of the two housings it is written D plus and the other is E plus. So D stands for this diode and E is the emitter. So the housing where D is inscribed, it is actually housing the IR diode, and the plus symbol signifies anode of that diode. And you can see on the other side, the plus symbol signifies the collector and E is the emitter. The emitter has to be connected to ground. Now if we look on the other side, we can find there are 4 terminals. Okay, these 2 terminals, this terminal and this terminal, they are for the diode and these 2 terminals are for the transistor. You can see here that one of the terminal is longer than all the other terminals. That is the anode of the diode. Okay. As usual, when you connect it to any supply, you have to use a resistance in series with the diode circuit. Otherwise, the diode may get damaged by excessive current. Normally, we apply a 12 volt supply while we are developing a circuit with the help of this slotted optical switch. And so far the collector is concerned, that is the collector of the phototransistor, what we do actually is we connect in series with the collector a resistance and then we connect the resistance to the supply, so that whenever there is an obstacle, you can find over here, if I put an obstacle in between the source and the detector, here the diode is the IR diode is the source and phototransistor is the detector. When there is nothing in this slot, then signal of the diode will reach that of the phototransistor, will reach the phototransistor. So the phototransistor base, we will be having the IR signal. So the transistor will start conducting. Now if you consider the resistance collector combination, then it is very clear that if there is nothing in between and we are trying to measure the voltage across the collector, that means in between collector to emitter, under the condition that a resistance is collected from the collector to the supply. In this case, let us consider 12 volt. So you see, if there is nothing in between, the signal from the diode will directly be reaching base of the transistor, and simply you will be getting no signal because the transistor is conducting, and you can simply apply the KVL. Now if I put an obstacle in between, suppose I have put this obstacle, so when there is the obstacle, no IR signal will be able to reach the phototransistor. So now what will happen? You can see the transistor will no more be in the conducting state, and when the transistor is not conducting, entire supply voltage will be reflected across the collector emitter terminal. So this is the basic funda of operation. If we take this object inside and now take it outside, we take it inside the slot, we are getting it outside the slot. What will we get? We will be getting continuous pulses. That means a pulse train. Now if this concept is understood, then the basic principle of measurement of RPM of this shaft is should be clear. Now see, for such measurements, this slotted disc is mandatory. You see, this is a very beautifully designed disc. This is the center where we connect the shaft of the motor, and you can see along the circumference there are equidistant holes, and the holes are completely identical. Now I will connect this uh, slotted disc to the shaft of the motor. It is connected, and now what I will do, I will just rotate it slowly by hand. Now you see, when it is rotating like this, what is actually happening? This is rotating in between the diode, that is the IR diode, and the phototransistor. When there is the hole, the phototransistor will be getting the signal from the diode. And when there is no hole, that is there is an obstacle, the phototransistor will be getting no signal. What does that signify? If I make proper measurement from the phototransistor, I will be getting a continuous train of pulses. If the rotation is at higher RPM, the pulses will be in such a format that you will have a higher frequency. And if this is rotating slowly, then you will be having a lower frequency at the output of the phototransistor. So this is the basic operation. Again the question arises, at the outset we had said that we are interested in measuring RPM of the shaft, and ultimately we are getting a frequency. Here again comes the problem of signal conditioning. We have to condition the signal in such a manner that this frequency can be converted to RPM. This needs complex circuitry undoubtedly. But here we are interested only to see the scheme of operation. We will be seeing that the frequency is proportional to the RPM. So we can say that if the RPM increases, the frequency will increase. If the RPM decreases, the frequency will decrease. Because if the RPM increases, the pulse train will be faster. That means the frequency will be higher. Now you see that we can simply use a frequency to voltage converter block or circuit to convert this frequency to voltage, and then we can calibrate that voltage using other electronic circuits, maybe using some op-amp based circuit to display the RPM. So that is completely a separate part of this entire instrumentation. Here we are only towards just detecting the RPM. Now you see there can be another method, quite interestingly. If we connect shaft of another motor, similar motor, if we can connect the shaft here, you may forget for time being this uh, disc. You can connect a shaft like this, axis to axis. Okay. So now what will happen when this motor will rotate? When this motor will rotate, that motor will also rotate. This motor is actually fed by the signal for its rotation, and that motor is rotating since there is a mechanical coupling in between this motor and that motor. So from the terminals of the second motor that is situated here, we will be taking out the voltage. Now you can simply see the voltage is directly proportional to the speed of this shaft, because faster the motor will rotate, more voltage will be induced. So this is another method, that is a Tacho method, but here we will be using this one. And okay, for this we have to take one connector. I will be using one relematic connector for this. Okay, this connector I will be connecting here. So you can see I have connected a connector very simply. That's a relematic one, and here there is a plug arrangement so that I can connect these wires directly to a 12 volt adapter. So this is the adapter pin. So I'll be connecting it like this. Now what will happen that this red wire will be supplying plus 12 volt. Okay. This black wire is connected to ground, and the brown wire is actually the output where we are expecting the pulse train, and this blue wire is nothing but ground, because we need a ground for our measurement. So we have to invite here the CRO in order to see the pulse. Okay, so I will be putting the CRO like this so that we can have a concurrent view of the motor and the CRO screen. So you can find here I am connecting this positive terminal of the CRO to the output pin, and we have to connect the ground as well. I have connected the ground now. Alright, so the connections are ready and we are in a condition to start our observations. Now you can see here, you kindly look at the screen of the CRO. I am slowly rotating the disc. You can see here, whenever there is a hole, now you can see you are getting a high signal. Now again you are getting a low signal. You will again get a high signal. Now you are getting a low signal. So you can see here that whenever the disc rotates, you are getting either high or low. Now if the disc start rotating at a considerable speed, you will be getting a train of pulses. Now this is very slow. You can see here, you are getting a train of pulses at the output. This is very slow thing, and you can see that the pulse width is varying because I am varying the speed here. Okay. Now you can see the train of pulses are there. Alright, now I will be not doing the thing manually. I will be applying some supply to the motor. You can see it has started, the motor has started operating, and you are getting the train of pulses here. I will be adjusting the time base. Now you can see train of pulses is very clear. You can see here. What is the frequency? 663.7 Hertz. Now what I will do, I will increase the speed of the motor. Now you can see the frequency has increased clearly. Again we can have the view of the pulses. Now that's the saturation for the speed of the motor. So now I will again lower the speed. You can find the frequency is also coming down. The motor will stop like this. So you can see that the frequency is directly proportional to the RPM. Now this concept is very important to understand that how we can use an optical switching arrangement towards measurement of RPM of a motor shaft. So if you come across any confusion in your mind, kindly comment and let us know so that we can get back to you with the answer at earliest. Thank you.